So as we said in the last video, chapter 4 is all about reactions in aqueous solutions. And in aqueous solutions, some things dissociate, some things don't. And that stuff that dissociated and didn't is more relevant to precipitation reactions, but it does apply to the other reaction types as well. Today we're talking about oxidation reduction reactions, also known as redox reactions. It's just combining oxidation and reduction into one word, redox reactions. So oxidation reduction reactions are electron swapping reactions. Somebody's got electrons, somebody's got electrons and doesn't want them. Somebody else doesn't have as many electrons as it wants, so you swap electrons between these two things. So in order to know who gains and who loses electrons, we're going to talk about oxidation numbers. And there's going to be rules in just a moment, but oxidation numbers will help us decide who gains and loses electrons. So number one question down here first, can you have oxidation without reduction? No way. Anytime someone gives away an electron, it has to give it to somebody else. So if one thing is oxidized, something else has to be reduced. Okay. So we will go through the rules of assigning oxidation numbers, but I will talk to you real quickly. This magnesium has no charge, so that would be an oxidation number of 0. In this compound on the right, the compound on the product side, magnesium oxide, it's a +2 charge. So magnesium went up in oxidation number. That means magnesium lost electrons. Remember, electrons are negatively charged. So losing electrons is called oxidation. So there's a couple of mnemonic devices to help you remember that losing electrons is oxidation. The one that I learned back in the day when I was sitting in your shoes is oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. That's the one that I learned, but your textbook currently refers to Leo the Lion Says Grr. Losing electrons is oxidation, and gaining electrons is reduction. So if magnesium went from a 0 to a +2, it increased in oxidation number, meaning it lost negative charges. Magnesium was oxidized. Magnesium was oxidized. There we go. Phew. Magnesium was oxidized. And I didn't say, but this oxygen has no charge. We'll talk about that. And it becomes an O2-. So it has 2 extra electrons in this compound than it did as an O2 molecule. So oxygen gained electrons. Therefore, oxygen was reduced. So again, the main point of this video is talking about oxidation numbers, yet I'm starting in a different place. I know I don't make sense sometimes. It's okay. So if we take that equation that we were given on that first slide and split it into the 2 separate equations that are happening simultaneously, let's do that. This magnesium becomes magnesium 2+. So if we separate it to magnesium becomes magnesium 2+, that's exactly what happened to the magnesium in this reaction. It's balanced up here already, so I'll carry my coefficients down. And 2 electrons were lost from a single magnesium, but because we have 2 magnesiums, 2 electrons are lost per magnesium. This is what's called a half reaction. Because it's the half reaction where electrons are the product, this is called an oxidation half reaction. Oxidation half reactions always lose electrons. If we do the exact same thing but the opposite, starting with oxygen and ending with O2-, we're going to put electrons on the reactants side of the equation. So we have 2 oxygens over here, 2 oxygens over there. This is balanced charge-wise because we got a 4- on this side and a 4-, 2 times 2 minus on that side. That's the reduction half reaction. Sum those things together, cancel out anything that can cancel, and all of a sudden we've got our equation that we had in the beginning. So writing these half reactions are things that we will do in this unit on redox reactions. But in order to do well with the redox reactions, you got to know oxidation numbers. So oxidation numbers are a way of pretending that electrons are completely transferred. Why do I say pretending? In ionic compounds, electrons are completely transferred. in molecules, electrons are shared. In ionic compounds, that's metals and nonmetals, electrons are completely transferred. In molecules, nonmetals and nonmetals, they're shared. But oxidation numbers always pretend like they are completely transferred. We'll talk about bonding and all that stuff later, but yeah. Well, let's walk through a couple of rules. Elements in their free, uncombined state have an oxidation number of 0. So that's sodium metal, beryllium metal, potassium metal, lead metal, hydrogen and oxygen as a diatomic. What other things are diatomics? Chlorine, bromine, iodine, fluorine, I2, fluorine, one more, nitrogen. There's a little top 7 on the periodic table. It's this guy, this guy, this guy, this one, this one, this one, and then hydrogen over there to the side. Those are my diatomics. So elements in their uncombined state, and those diatomics are all uncombined states. This is the natural base state of phosphorus as well. There are some other oddities like that. We won't talk much about those. Monatomic ions. The oxidation number is equal to the charge on the ion. Well, if lithium is a 1+, the oxidation number is a +1. If iron is a 3+, the oxidation number is a +3. If oxygen is a 2-, if oxygen is a 2-, the oxidation number is -2. Whatever the charge is, that is the oxidation number. So we will often be given things where it's combined like so. The sodium in this ionic compound has a charge of +1. The oxygen in this compound has a charge of -2. So the oxidation number of sodium is +1. The oxidation number of oxygen is -2. Okay. The oxidation number of oxygen is always -2. Always -2. Except in a couple of rare circumstances. But oxygen is almost always -2. Almost always. When it's uncombined, it's a 0. And in these other states, it's a -1. Okay. Group 1A metals are always +1. Lithium, sodium, potassium, cesium, rubidium. Group 2A metals, +2. Beryllium, manganese, calcium, strontium, barium. Fluorine's always -1. The other halogens, that's chlorine, bromine, iodine, those can all change, but fluorine is always -1. As a little side note here, that's due to electronegativity, and it will be all the way until chapter 9 until we say more about electronegativity, but that's why fluorine is always -1. The oxidation number of hydrogen is always +1, except when it's bonded to something like an alkali metal or alkaline earth metal. So these are alkali, and these are alkaline earth. So lithium hydride, the lithium was already a rule we've talked about. So the lithium is a +1. That means the hydrogen has to be a -1, because if I skip ahead, the sum of the oxidation numbers always has to equal the charge on the molecule or the ion. So this thing is a 0 charge. So if lithium is a +1, it has to mandate hydrogen is a -1. Calcium hydride. Calcium is already in a higher rule. Calcium is a +2, so that hydrogen has to be a -1 so that those oxidation numbers can balance out. The sum of the charges has to always equal the sum on the molecule or the ion. So if we're talking about HCO3-, according to our rules, what numbers do we know? We know that oxygen is always a -2. Always a -2. Unless it's uncombined as a diatomic, or H2O2, or O2-2-. Hydrogen is always a +1, unless it's in a binary compound like these up here. This is not a binary compound. So, carbon is not part of my rules. Carbon could be multiple charges. How do you figure out what charge carbon is? Well, hydrogen is +1, plus whatever charge carbon is, plus oxygen is -2, but you've got 3 of them, and all of that has to sum to -1, which is the overall charge of your atom, overall charge of your molecule, your ion. Solve that thing, and you get carbon as a +4. So carbon, like many of the nonmetals up in the corner quadrant of the periodic table, carbon can be a lot of different oxidation states, and it changes oxidation state based on who it's connected to. We use all the other rules to help identify what carbon's number is. We knew oxygen, we knew hydrogen, solve for your unknown carbon. So if we walk through a couple of these, what do we know about this first one? We know sodium is a +1 because he's an alkali metal. And oxygen is -2 because he's not in one of those weird states. And iodine can be various numbers. So I've got +1 plus unknown iodine plus 3 times -2 for my oxygen equals 0 because there's no charge written up here. So solve for iodine, I equals +5. Yeah? Iodine can be a lot of different oxidation states. What about IF7? If we say, I know F is always -1, and I need to multiply that by 7. So this is where students get confused a little bit sometimes. The oxidation number of fluorine is -1. The reason we're multiplying by 7 is to help us deduce what the charge on I is, what the oxidation state of I is. But F itself is -1. So when you're asked the oxidation number of fluorine, it's -1. It's not -7. Okay. So in order to equal 0, it must mean that I down here is +7. Iodine can change oxidation states depending on who it's connected to. And when it's IF7, it's a +7. Let's do one more. We'll do this bottom corner. The top one I kind of think is in your chem activity, but I can't remember exactly. So oxygen's -2. Hopefully you can spit that out as quick as I wrote that out. Potassium is +1. So I've got +1 times 2 plus 2 times unknown chromium plus 7 times -2 equals 0. If I walk through all the math, we got -14, 2 chromium, +2. I got 2 chromium equals 12. Did you follow me? So each chromium must be a +6. Yeah? Yeah. It's just a little algebra. You can solve that guy on your own. That's good enough to get us through the first chem activity, which is assigning oxidation numbers. But we're doing another one this time as well, but we'll make that in a new video.